It's Andre from High Performance Academy here. Welcome along to another one of our members' webinars. And today we're going to be talking about selecting the correct parts for your next engine build. And this is something that I see so many people get wrong, particularly when I ran my old workshop. We'd see customers bring us either engines that had already been assembled, or for that matter, they'd bring us engine parts to assemble, and you'd look at the list of parts, you'd look at the customer's application or what they were trying to achieve, and you just knew that the two were not compatible. So at worst, if it's not picked up early enough, this can end up with an expensive engine failure. And at best it's still going to end up wasting a bunch of money. So it is one of those things that really does require you to put in a little bit of thought at the start and make sure that you're really clear on your aims and your intentions, and this way this is going to help you select the parts that are going to be most suitable for what you're trying to do. As usual, we will have questions and answers at the end of the lesson, so if there's anything I talk about, please ask those in the chat and we'll get into those at the end. Now, I think it's probably also worth saying here, sometimes we do get ourselves into an unavoidable situation with a project car build that our aims do move, and we can do our best at the start of a project to kind of envisage exactly where we're going and be as clear as we can, but sometimes, particularly with those projects that are sort of a longer term build, the goalposts do tend to shift. It's just important to keep track of that. We obviously want to do our best to really clearly define our aims at the start, but if those goalposts do shift, just make sure that you keep stock of that and decide if maybe some of the parts you've purchased are no longer going to be suitable for your new goal. It's going to be much cheaper to offload those second hand and buy the correct part than it is to repair damage to your engine because those parts have failed in service. So what we're trying to do here is essentially the same as anyone. What we want to do is get the best bang for our buck. So we want to get the best performance out of our engine that we can, along with great reliability, without necessarily spending a fortune. And this can go both ways. I see probably more people try and achieve power targets or applications that really aren't something that the parts that they've purchased are up to. But occasionally we see the other side of that as well, where people have spent a huge amount of money on parts that are just well and truly above the level of what they actually needed to achieve the task. Case in point is engines where people have built a full engine with aftermarket forged pistons, connecting rods, and even billet crankshafts to achieve power aims that I know well and truly could be achieved on completely stock parts, provided that the engine is tuned correctly. So those are the two things we're sort of focusing on here. Reliability obviously is key, and I need to really talk about what that actually means, because reliability is different to different people and it's different for different applications. Obviously, if you're building a lightly modified street car, you would quite rightly expect good long-term reliability. If I'm building an engine for a modified street car that's going to make maybe 20 to 50% more power than stock, I would be expecting that engine to last 50,000+ kilometers of use without needing to be pulled apart. On the other hand, if you're taking a small capacity 2-litre 4-cylinder engine and you want to take that engine drag racing and you want to challenge for world records, and you're looking at producing 14 or 1500 plus wheel horsepower and revving it to 11,000 RPM, chances are you're not going to be getting 100,000 miles between oil changes. The reality is very different, and an engine at that level, no matter what parts are going into it, no matter how much money you're spending on it, there's a pretty good chance you're going to be pulling that engine down between meetings during a racing season. So it's very important to be realistic. I think both the internet and car magazines have skewed enthusiast views on what is actually realistic here and what can be achieved. A case in point here, talking to JR from Extreme Turbo Systems over in the US at the Pikes Peak airstrip attack a couple of years ago. ago, and ETS are very famous for their work on the R35 GTR platform. And again, records change, but at the point we were talking to them, they had the half-mile world record for the R35 platform. That particular engine produces somewhere in the region of 3,000 wheel horsepower when it's set up on kill. And the reality of that, I can't remember the specifics now, but I think they were getting somewhere in the region of 12 passes on a bottom end. And I'm not talking about cheap parts here. This is a Sonny Bryant crank, basically the best that money can buy. The same with the conrods and also the pistons. The valve train would only do about twice as many passes. So you just need to factor that in. If you want to go fast at that level, then it is going to cost you, and you do need to factor in the maintenance costs that will be associated with that. And again, just because I've been talking about the R35 platform, again, there'll be people here that argue this, but JR's sort of experience suggested that if you want actual reliability where the engine is not going to need to be pulled apart regularly, then his line in the sand was around about the 1,300 wheel horsepower mark. Once you go beyond that point, then things are going to end up breaking and they are going to end up failing. So the other thing I'll mention here, because it is such a big factor in engine performance, is turbocharger consideration. So obviously the amount of power that we can produce is a factor of the engine, but ultimately the engine is there to produce airflow through the cylinder head. That's key. Also, the bottom end is there to support that power, make sure it's going to remain reliable. But then when we're talking about turbocharged engines, the turbocharger can play such a big factor in how much power ultimately the engine will produce. It's a very different aspect. It's really not related to our topic today, so I'm going to mention it in passing there, and from there we're going to leave that alone. Alright, so let's talk about how we're going to go about deciding on what parts are suitable for our project. I'm going to go through sort of a couple of worked examples, if you like, here for a couple of engine builds we're doing in-house, so you can see how I apply this process. But first of all, what we want to do is know what we're trying to achieve. Obviously, that's the key thing. We need to factor in what we're trying to achieve in terms of our power output. We want to also consider the RPM range that the engine's going to need to operate in, where we want the power band as well within that RPM range. It's no good for a street engine if we don't make any power below 7,000 RPM and we need to change gear at 8. That's not really going to make for a very fast car on the street. We also need to consider, like I've mentioned there, what are we expecting in terms of reliability or maintenance requirements, because that's going to be a big driver there in how we go about this and how much power we're going to make. So once we've got all of these factors sort of clear in our mind and we've got an understanding of them, how do we decide what parts are going to be suitable? One of the more expensive ways of going about this would be trial and error, basically selecting parts with no previous understanding of what the parts have been proven to support and putting the engine together and seeing how it works. Now that might sound a little ridiculous, and the reality as we'll move through this is these days it's really not necessary. However, in saying that, if we're building an engine that is a popular engine and we're aiming for a realistic power level, and I'm talking here probably something in the region of a 50% improvement in power, maybe even a little bit more than that, then using mainstream off-the-shelf parts from recognized suppliers for pistons and connecting rods honestly is probably in most instances going to be absolutely fine. We do not find too many manufacturers who are sort of fly-by-night companies setting up forgeries to make pistons and to make connecting rods. It's a huge investment in capital to produce a factory to make these parts. So generally you don't see companies sort of come along and then disappear too quickly. The mainstream ones that we've probably all heard about, they've been around for a long time. Chances are they're going to be around for a long time in the future. So their parts almost certainly are going to be up to the task if you're looking for modest improvements in power. The other way though that's probably a little bit easier, Again, if you are dealing with a common platform, and this is going to be the case for most people unless you're dealing with a brand new engine straight off the showroom floor that really no one has experience with. And this actually happened with the new Supra, of course. When that came out, no one really had experience with that BMW engine, so we quickly saw a few companies over in the US sort of battling for supremacy, who could be the first to 1,000 horsepower, etc. So that's slightly different. There you are really finding your feet, and there you're drawing probably more on personal experience and what you've seen work with other engines. But for those who are at least dealing with an engine that has a bit of history, we can rely on some pretty well trodden paths where people have a formula of parts that work. So the example is a perfect one here. The two engines that we're going to be going through will be 4G63s, and these are a very old engine now, thousands of these built, and basically any combination you want from sort of a 300 horsepower stock rebuild through to 800 horsepower streets and strip through to 1500 plus wheel horsepower world record drag cars. Everyone's done that. It's been done numerous times. There's not a lot of secrets there in those builds, so that makes it easy. Probably the hardest part there is you're going to probably spend a fair bit of time searching through enthusiast forums for that particular platform and trying to work out fact from fiction, because even with those formulas, everyone's going to be using slightly different parts. The last option here is rely on advice. Now, this can be hit and miss as well, so it needs to be understood. If you are going to be dealing with a performance workshop for your build, then I'd strongly recommend that you approach a performance workshop that is well experienced with your particular platform. Someone that's actually got runs on the board, they've got some evidence that they know how to build a combination at your particular power level. And then, of course, if they're in that situation, then yes, you should be taking their advice, particularly if you are going to be getting them to do the assembly work. Then it's a little bit of a hollow aspect if you come across to a performance workshop, ask them all of their advice. They tell you to buy XYZ product, and then you go and buy something completely different, and then ask them to put it together. It's probably not going to be a real good result, and it's not going to be a really good experience. Even when you've got advice or you've gone through the internet forums, as I mentioned, there's likely to be some options available. So we're going to take you through two builds now so we can sort of explain things here in a bit more detail, how my own thought process works, how I've drawn from my own experience and the experience from others with these builds. So two 4G63 builds, although two very different builds. The first one we're going to look at, this is an engine that we're piecing together for a Mitsubishi Evo 9. We don't actually have the car for the engine to go in yet, but that's a story for another day. This will be a worked example that's going to go into our practical engine building course once it's finished as well. We've been having a lot of people ask for Mitsubishi 4G63 worked example information. So it's a very popular engine, understandably. So let's start with our aims for this engine. We're going to be looking at an ability to produce somewhere in the region of about 700 horsepower at the flywheel. Now that might sound pretty high, but that's not a huge stretch for the 4G63 engine. It's been well proven to be able to support that sort of power level with actually relatively modest modifications. Again, some of this comes from my own experience, but if you don't have that experience, it's not going to be hard to see numerous examples out there on enthusiast forums or magazine covers that are achieving similar results. To go along with that 700 wheel horsepower, we want a rev range or a rev limit to 8,000 RPM. Again, not a big stretch here from the factory rev limit around 7,500. We just want to push that a little bit further out. And it is important when we are considering the rev limit there, as the rev limit or as the RPM increases, we see the load on the components increase exponentially, expensively as well, I guess you could say, but exponentially. So the lower we can keep our rev limit, the easier it's going to be on our engine components. So that's a factor that I like to consider there. Other aspect with this engine is that we will be retaining a wet sump lubrication system. Now this is for simplicity and cost savings, also because the car is not going to be a circuit car which will see sustained high lateral g-forces, but even on the street with a modified Evo, the factory wet sump is potentially problematic, and we will probably end up taking this to the odd track day or running it up a hill climb. So we want something that's a little bit better than stock, so we're going to need to address that. Ultimately though, it is not a race car, so it needs to be streetable. So this is going to drive a lot of our choices. It would definitely drive our turbo selection, although as I've mentioned, I'm not going to dive too much into that from here on. And what it does mean though is I want a good usable power band. I want something that's going to have good power from about 4 to 4,500 RPM all the way up to 8,000 RPM. Other considerations here to help with the 700 flywheel horsepower power target, it will be a flex fuel compliant vehicle. So we're only going to be making the 700 horsepower on probably E85 or at least a fairly high ethanol content blend. And that also drives some of our considerations around compression ratio as well. So those are our aims there. That's kind of like my shopping list of what I want the engine to do. So then we've got some choices that we can go through on how we can get a combination of parts that's going to do that. And the 4G63 actually probably gives us a few more options than most in terms of capacity and block configuration or block options. So I'll dive into this, and for those who aren't familiar with the 4G63 world, I'll try and explain it as best I can. First of all, we have the option of using the 4G63 block, which is a 2-litre engine block, or we can use the 4G64 block. So the 4G64 has a larger bore diameter and it uses a 6mm taller block to go along with a 100mm stroke crankshaft. The factory 4G63 crank, on the other hand, is 88mm. So 2-litre or 2.4. Now, on face value, you might be thinking, well, capacity's king there, so 2.4 would be the choice. I've built a lot of 2-litre combinations. I've built a lot of 2.1, 2.2 and 2.4 litre combinations, and this is where it comes down to personal preference. I'm not saying there's anything strictly wrong with the 2.4 block, but there are a couple of considerations I keep in mind. Firstly, the 4G64 block at stock bore size, we're at an 87mm bore. 4G63, 85mm bore. So some of the capacity increase comes from the increased bore diameter, some of it comes from the increase in stroke. The problem with the increase in bore diameter for me is that we're still at the same bore centers between the 63 and the 64 block. So what this means, and I wish I had one here to show you, is that we end up with a very thin wall between adjacent cylinders, and this can be problematic in my experience with head gasket sealing. The other aspect it gets a little bit tricky with is our actual bore thickness and bore strength, and it also means that we are limited in what we can do. Now, when I am starting with a fresh build, what I'll generally do where possible, and this is easy with a cast iron block, is I'll go to a first oversized piston, which is 20 thousandths of an inch or 0.5 millimeter larger than the factory bore diameter. And the reason we do this is that then it allows us to take what could be a factory high mileage engine, and we get our machinist to bore and hone the block. That allows them to remove any wear in the existing block. It allows us to get back to a fresh home pattern, the correct piston to cylinder wall clearance, and we know that our rings are going to bed in well on that fresh home pattern. So 85mm, we're going to go to 85.5mm. Still gives us a good amount of wall thickness. When we're at 87mm, we go 87.5. That's making that problem with the thinness between the cylinders even worse. So don't get me wrong, it's not something we cannot do. There's plenty of high powered 4G64s out there. It's just a consideration that I keep in mind. The other factor though with the 4G64 is the 100mm stroke. On paper, piston speed, the rod to stroke ratio, it's not a well suited combination to high RPM. Again, I've built plenty of 4G64s which we have run to 8 or even 9,000 RPM, but it's not something that is really ideal. and what we can get away with for a drag application where it's only doing a 8-second pass down the drag strip compared to something that's going to be driven on the street and revved regularly. That's another consideration. So my personal preference is to stick to the 2-litre block, 4G63 block, and I do want some more capacity in here, so what I'm going to do is go somewhere in between. Stock crankshaft 88mm, they've got the 64 crankshaft which is 100mm, and there are now plenty of aftermarket crankshaft suppliers that do a 94mm crank, which takes us to 2.2 litres. So I'm going to split the difference there, and that's what we're going to do with that. It's going to give us a nice improvement in our boost response. It's going to bolster that low RPM torque, which comes back to my desired power band 4.5 through to 8,000 RPM. It's still going to have absolutely no problems with running to high RPM. The rod to stroke ratio, yes, it's still not ideal, but there is a limit to what we can do with rod to stroke ratio when we are dealing with factory parts. So how do we get around this? We've now gone from an 88mm crankshaft to a 94mm crankshaft. So what we need to do there, if we ran a factory 4G63 piston, it's going to come out the top of the bore at the top of the stroke. There's a couple of ways we can get around this. We can use a shorter connecting rod. Or alternatively, we can move the piston higher in the bore. So that's what we're going to do here. This is not for that build, but let's just have a look at this piston under the overhead camera. So this is our wrist pin here. The distance between the center of the wrist pin and the deck of the piston, the deck surface of the piston, this is called our compression height. So what we do is we just move the wrist pin higher in the piston, and we can actually see that this intersects. It's probably a little difficult here. It actually intersects through the oil control ring there. And that's absolutely fine. There's nothing wrong with that. All we do is use an oil ring rail support on the base of that, and that allows us to retain the factory 4G63 150mm long connecting rod. So by going from an 88mm stroke crankshaft to 94mm, we've increased our stroke, we've kept the rod length the same, so we've actually made our rod to stroke ratio worse than the stock 4G63. But again, this is about compromise, and it's a combination that we know works because we have proven it. Now we'll talk about the block here. So I've mentioned that we're going to go 4G63, so that's easy. If we can source an Evo 9 block, then that's even better. One of the differences with the Evo 9 is on the back of the block there is an oil feed to the Myvec system on the cylinder head. So Myvec is Mitsubishi's take on continuously variable cam control, and it needs an oil supply off one of the galleries to allow that to work. Now, that's not to say we can't use a non-Evo 9 block and then add that fitting. Depending on what generation of block you are using, if you're going a bit earlier, then there are some differences in the water pump as well. So those are a few idiosyncrasies in the 4G63 world. So with the crankshaft there that's going to go into that block, we're going to be using a Manley 94mm billet crankshaft. Now, this is probably a good time to just talk about our crankshaft options, because if I was staying 2 litre, I actually, for this power level, wouldn't necessarily need to switch to an aftermarket crankshaft. And this is one of those areas where I think people sometimes can be lulled into a sense of requiring these parts that may not be completely essential. So let's look at why that's the case. And this gets a little bit tricky, because what we need to do is actually come back to what things were like a fair while ago. So if we jump across to my laptop screen, actually that's the wrong one, but let's see if I can show you. Okay, this is a comparison here between a forged and a cast crankshaft. So many years ago, probably the majority of engines that we would be rebuilding used what is referred to as a cast crankshaft, and that's the crankshaft that we can see here on the right. Casting, basically the process you could liken to pouring molten metal into a mold in the shape of a crankshaft. There's a little bit more to it than that, but essentially that's what's happening here. And what it results in is essentially no real grain structure within the finished crankshaft, and this means that there isn't a lot of strength in the material. Obviously, that's not an ideal scenario for a crankshaft. We see the same with a cast connecting rod, and the crankshaft can end up failing if we increase the power level or we increase the RPM range. And a really easy way to tell if you're looking at a forged crankshaft or a cast crankshaft is this one on the right here. We can see the parting mark there, the casting mark along the crankshaft that I've just circled. So that sharp mark, where it looks like literally two pieces of a mold have come together, that is the casting mark, and that denotes that we've got a cast crankshaft. On the left hand side, we've got a forged crankshaft, and it's a little bit harder to see, but we'll go back to that earlier shot in a second. The forging mark is a lot wider, so very, very different between a cast crankshaft and a forging. Very, very easy to tell what you've got. The forging, without getting too deep into it, this is where essentially the material is forced into the shape of a crankshaft under intense heat and pressure, and this creates a really rigid grain structure within the finished crankshaft, which is much stronger when we're applying more power to the finished component. Let's see if I can get back. There we go. Now we'll just zoom in on this. I think this actually is a 4G63 crank as well at a glance here. So again, hopefully you can sort of see this. That mark there on the crankshaft journal, that is the forging mark. And again, you can see that it's about 10 or 15 millimeters wide versus that really sharp mark that we had on the cast crankshaft. So what's the point in talking about this? Well, the reason I want to mention this is that if you're dealing with an older engine that had a cast crankshaft and you want to make a lot more power, yeah, the crankshaft almost certainly is going to have to go. With late model performance engines that come almost certainly with a forged crankshaft from stock, these crankshafts are actually incredibly strong from the factory, and there may not be a requirement to actually replace them. So in terms of the 4G63 world, I've actually run the factory Mitsubishi 4G63 crankshaft at in excess of 1,000 wheel horsepower in my own drag engine. We actually found at the time we were getting very similar crankshaft life expectancy on the stock crankshaft versus some of the billet components that we were running at the time. And the difference was that I was paying about $4,000 for a billet crankshaft, and I was paying about $1,100 for a factory crankshaft. Basically, what we were doing is pulling the engines down at the end of a season's drag racing. Both would end up exhibiting cracks in the fillet radius of the crankshaft. So at that point, as soon as you know that they're cracked, you obviously can't in good conscience put them back in an engine. So we're looking at replacing a $1,100 crankshaft or a $4,000 crankshaft. Basically, it's a no-brainer. Now, that's not to say that's always going to be the case. We would, of course, get to a point where the factory crankshaft wouldn't be able to handle it. But since I know full well that I can make over 1,000 wheel horsepower with a factory crankshaft, I have no concerns at all making 700 flywheel horsepower on the stock crankshaft. So that is a consideration that we need to make there. All right, I'll just head back to my notes now. In terms of connecting rods, so we've talked about the crankshaft, we've talked about the block. In terms of the connecting rods themselves, again, 700 horsepower. We're not at a point here where we need anything particularly exotic. So basically any of the off-the-shelf common stock con rods for the 4G63 will be up to the task. So in this case, we're going to run a set of K1 Technology rods. We've been using these with really good results in our Nissan SR20 turbo engine. And one of the things with the K1 rod that I do like is that they're actually really light as well. So that's a nice advantage. Often we go to an aftermarket component, and in order to get the additional strength, the aftermarket rod ends up adding a lot of rotating weight to the engine assembly. So obviously we need the strength in there. So if there's no other way around it, then yes, we may have to settle for a component that is a bit heavier. But if we can get a stronger component that doesn't add any weight or is in fact lighter, happy days. I'm definitely going to take that every time. With these K1 Technologies rods, as we'd see with most aftermarket rods, they do come balanced from the factory, or at least within a tolerance. I generally like to tighten that up a little bit, and I always at least check what we're dealing with as well. Our policy here, trust but verify. Also commonplace with most aftermarket rods, they use the ARP 2000 rod bolt. So again, absolutely nothing wrong with that rod for our application. It's going to do the job just fine, and it's a pretty cost-effective option. One of the considerations that people overlook as well when selecting a rod is how the rod will stand up to the various forces that they're going to be applied to the rod in operation. So the obvious one is the compressor force, where the piston or the combustion pressure acting down on the piston through the rod is basically trying to push the two ends of the rod together. So the rod needs to be able to withstand that in order to put up with the power that the engine is producing. It's really cylinder pressure that's affecting that, but this is what we're increasing. We're increasing that cylinder pressure when we want to make more power. The other part, though, that's easy to overlook is that when we increase our rev range, the conrod is being placed under some very different stresses, and that's where the conrod needs to actually change direction as the piston goes past top dead center on the exhaust stroke. So the piston weight then needs to be slowed down by the connecting rod and needs to change direction and be accelerated away from top dead center. So it actually puts tensile force into the rod, which is where it's being trying to be torn apart. So a consideration there, and I don't need this at our current RPM target of 8,000, but this is something that we did choose for our SR20, given that we're running that to 9,000. I'll jump over to our overhead shot. These are a custom age 625 plus rod bolt from ARP, so it's made from a much stronger material that can provide a lot more clamping force, because it is the little rod bolt on the bottom of the connecting rod that's one of the most loaded parts at higher RPM. So that's a nice little insurance policy there. If you are going to change rod bolts, it's not always going to be the case, but because of the additional clamping load, that can also affect the journal diameter, or basically can deform it so that the big end journal and the connecting rod is no longer perfectly round, which in turn can influence your bearing clearances as well. So it's a good idea to have your machinist check that if you can't do it yourself. They may need to hone the bore to get it back round with the stronger bolts there as well. Pistons, now I don't actually have them here, but for this particular build, what we're going to be doing is running a JE forged piston, and we've used JE forged pistons through our builds over the years, and I've had really good results with them. So again, nothing particularly special that we need to consider here. 700 horsepower for a good quality 2618 forging should be no problem. Couple of considerations. We'll get this piston under our overhead shot here. And I don't have this for the 4G63. This is a FA20 piston. It'll give you an idea. What we can see is this has a anti-friction coating applied to the skirt here, pretty typical with a lot of JE's shelf stock pistons, or you can ask them to apply it. So that's nice for a street engine. It's going to give us a reduction in friction there. The other option, which again I can't show you, is JE offer what's called an asymmetric side forging, which is where the parts that run against the cylinder wall are asymmetric in their size or width. So basically they put more diameter into that component where the piston is being forced into the cylinder wall on the thrust face, and less on the other side of the piston. So basically, again, just reducing the frictional losses. Now you need to factor this in, because that style of piston does reduce the weight of the piston, which is a good thing, but it also is not going to be the best option if you want to make really high power. So around that 700 horsepower mark is where the asymmetrical side pistons are sort of recommended. That's about the maximum power level you should be running those at. Another option there as well, which is worth considering, and I'll show this in a bit more detail, is the wrist pins that we can choose. So if we look at a couple of wrist pins here, the one on the left here, this is actually for the drag engine build that we're going to go over next. So what we can see here is the thickness of the wrist pin material versus the shelf stock wrist pin that I've got in my right hand. So as our power levels increase and our RPM increase, we find that the wrist pin can actually start to distort. So it can be worth considering moving up to a thicker wrist pin just for strength for that sort of an application. So that's our component. So again, nothing really out of the ordinary there. We're just relying solely on quality shelf stock components. We're not trying to do anything particularly extreme here. 700 horsepower again, not a particularly high power aim. A couple of specifics though for the 4G63. These engines do run under piston oil squirters in stock form. I quite often get asked if it's a good idea to remove those, and I know there are two schools of thought on this. One of those schools of thought is that removing the under piston oil squirters is going to mean there's less oil being splashed up under the piston, which can in turn increase oil consumption, and it's also going to provide more oil to the bearings, which is where it's needed. Personally, I've run under piston oil squirters on all of my 4G63 engines, including my drag builds. I like the idea of the oil mist being able to cool the underside of the piston as well, and I've never had any problems with excess oil consumption. So I've basically found good results with the under piston oil squirters. I tend to stick to them. One thing I will do though in a 4G63 engine is I will remove the balance shafts. Now there are two balance shafts in the 4G63 engine. One runs off the back of the factory oil pump. It is commonplace to cut that off at the back of the oil pump and then use something like a pressure plug or 8th BSP pressure plug to blank the hole that runs down through that shaft. This is not my recommendation. The problem with doing this is that it basically doesn't leave any support for the balance shaft for the oil pump, and that can, I'll just try and find this while I'm talking, that can end up in premature failure of the oil pump, and I've seen this numerous times. So there we go, this one will do. If we head across to my laptop screen, instead of doing that, oh that's great, it's not going to work at all. There we go. This is what it looks like here. So this is basically a factory balance shaft where the weight has been removed or machined off it. You can do this with a factory balance shaft. You don't actually need to buy anything flash. Other companies, like this is one from Boost and Performance. No, that's another factory balance shaft that's been machined. Some companies do actually make their own complete replacement, but it's really not necessary. Basically, how it works is the section here runs in the balance shaft bearing in the block. And this little section here runs through into the oil pump. So always make sure with the 4G63 engine that you're not just lopping that balance shaft off. It's going to end up causing you premature oil pump failure if you do so. The other balance shaft, on the other hand, that is belt driven, that just simply gets removed. But another little trick there is that the bearings in the block are actually fed off the main oil gallery. So if you just remove that balance shaft and do nothing else, you're going to end up with very low oil pressure. So really easy. All you need to do there is have your machinist tap out the existing bearings and then turn them 90 degrees and then tap them back in. When they turn them 90 degrees, it'll just blank off the hole in the block there and prevent you losing your oil pressure. So that's something I'll do on all 4G63s. I do quite often get asked, so what's that going to do to the vibration in the engine? Oh yes, you will generally find that an engine that has had the balance shafts removed will be a little bit harsher in operation than stock. But I also go through and balance all of the components inside the engine as well. So generally, I don't find my results too much different to a stock engine. You've got a little bit of additional power comes from removing those balance shafts. Not enough to really be too worried about, but the other aspect is it does improve reliability because these balance shafts in high mileage engines are known to be a little bit problematic as well. Right, so baffled sump, I did talk briefly about that. There are companies around that do baffled sumps for these. We're going to be using a local company here that modifies the factory sump. AMS, I just looked at their balance shaft kit when we were trying to find those photos before. I know they do a baffled sump for the 4G63 as well. So just a good quality sump that's going to add some baffling and a little bit more capacity for my application. That's all we're going to be needing there. A couple of other considerations. We will be replacing the factory main bolts and head bolts with ARP main bolt, main stud kit. That's just a ARP 8740 material, so just their shelf stock kit is going to be absolutely adequate for that application. With the ARP head studs, we're going to retain the factory 4G63 11mm stud, but we will go to their superior material which is L19, and we're going to couple this with a MLS gasket. So that's one of the other sort of really big considerations when we are dealing with head gasket set on a turbocharged engine. I'll get this under our overhead camera. This is actually SR20 from Tomei, but basically you get the idea. It's very similar. So not a huge issue, given that the late model 4G63s actually ran an MLS gasket from stock, and people do quite often utilize those gaskets. I personally have had really good results with the likes of the HKS MLS gasket for the 4G63s, and I tend to stick to what I know has worked in the past. So that really covers our bottom end build. Move on to the cylinder head, because this is an area where we can end up spending a huge amount of money. In our case, again, with our relatively modest power aims, we don't need to go too crazy here. We can actually make these power levels basically with a completely stock head with some cams, but this will affect our turbo selection and will affect the boost pressure that we need to run in order to get that power level. At 700 horsepower, a porting program, maybe CNC or hand porting, would be nice, but it isn't 100% essential, and you can spend a lot of money on head porting, so it's something you really do want to consider. Likewise, do you want to go to an aftermarket valve? Again, not 100% necessary at this point, particularly for a street application that's not going to be a serious competition car. We've proven that the factory 4G63 valves are actually pretty reliable. If I was going to be more erring on the side of competition, I'd probably go to an aftermarket valve, and at that point you might as well go to a 1mm oversized valve, because there is some potential improvement in port flow through those as well. In our instance here, the main modification we are going to be making is to our camshaft. So we've got some GSC Power Division cams. This is the GSC S2 cam profile, and we've got that cam sitting here. So it's a full billet camshaft, pretty well proven for the 4G63 Evo 9 engine. And with the Evo 9 engine, we do need to be a little bit mindful of the fact that the MyVex system does limit what we can do. So generally with a continuously variable cam control system, it's great because it fills out that bottom end in terms of torque and power, works well with our power aims, but it also limits the size of the cam profile we can use, because we end up in a potential problem with valve-to-valve contact if we can move the camshaft too far. So again, the S2 cam, pretty well proven. This is an area where we do need to be mindful as well, because it is really easy to just jump on a camshaft manufacturer's website and choose the biggest, baddest camshaft that they make for a particular engine. That is probably not going to work too well. Yes, you may make a little bit of additional power at high RPM, but the reality is that for our application, I've already highlighted, the power band is more important to me. So I'd prefer to sacrifice a little bit of high RPM performance to fill in that low RPM, and that's not going to end up being what you'll get with the biggest, baddest cam that they make. So this is where understanding the cam profile, talk to the manufacturer and give them your exact aims, and This is where being realistic about your target and not trying to get a dyno horsepower figure to impress your friends with. It's actually going to give you a car that's going to be more fun to drive and ultimately faster on the street. So GSC S2 cams. The other thing that we do need to be mindful of with cams is that we need a matching valve spring. So again, GSC Power Division, if we go to our overhead camera, they produce a drop-in spring kit for that particular cam. So always a good idea, no matter who you're using for your cams, make sure you use their recommended valve spring kit. The valve springs need to be selected to suit the cam. If not, you can get into some serious problems there. The valve springs there also come with a titanium retainer. Pretty much industry standard these days. Is not a lot of valve spring kits you'll get that won't come with a titanium retainer. So basically that's our combination there. Nothing too over the top. So you'll note that we haven't gone crazy on the cylinder head, and we're using relatively cost-effective shelf stock parts for our pistons, our connecting rods. And while we have gone with the expense of a billet crankshaft, the reason we've done this is because it is giving us the extra capacity that we need, and we need to weigh that up. Do we want the extra expense of the stroker crankshaft to give us that extra bottom end from the extra capacity? In this case, we've deemed that that is going to be beneficial. So there you go. That's our first build and the process that I've gone through, trying to get good results without breaking the bank. Next one, and I will move through this a little bit quicker because a lot of there's a lot of crossover here, but this is for our drag Evo engine build. So if you have been hiding under a rock for a while, you're probably not, you may not be aware that before we founded High Performance Academy, I was pretty heavily involved in import drag racing. And if we head across to my laptop screen for a moment, this is my old shop car. It's a Mitsubishi Lancer Evo 3. At the time this car was retired, it held the world record for the fastest Mitsubishi Evo four-wheel drive, and it ran as quick as an 8.23 at 180 mile an hour. Now that was probably about 10 plus years ago now, so yes, times have dropped significantly. Got several competitors now in the 7-second zone. I think last time I checked drag times, I was probably about 11th or 12th fastest still, which I thought was probably still pretty impressive. Given that what we were doing back then, we didn't have the benefit of billet blocks, which are so common now, and we also didn't have the benefit of the turbo technology. However, I've held on to this car. It's sitting at Highlands Motorsport Park at the moment in the museum gathering dust, and we thought it'd be cool to bring this back and do a bit of a build through High Performance Academy. We're going to be covering this again in our engine building course and in our tuning courses. Don't worry, it's probably not likely to be hitting a drag strip, at least definitely not going to be chasing down any world records anytime soon, but it would be nice to have the old girl back up and running. So what do we need for a build at this level? The first thing to probably discuss here would be the engine blocks, because these days, as I kind of just touched on, billet blocks have become so common. So again, head across to my laptop for a second. So this is a typical billet block. This one here, I think, is either 2JZ or RB, can't quite recall. But yeah, manufacturers now, there's a handful of them around the world making these blocks, and they're actually becoming reasonably cost effective. I think off the top of my head, the 4G63 block from Bullet Race Engineering is somewhere in the region of about 10,000 Australian dollars, and that comes with sleeves and it comes with ARP hardware for head studs and main studs. That might sound expensive, but when you're looking at a build that's going to be producing 1200 plus wheel horsepower, it can be pretty cheap in the big scheme of things, particularly if you're going to keep that block a little bit more reliable. Now, we like to make our lives a little bit more difficult for ourselves, and we don't want to go down this route. A couple of reasons why. First of all, we know that more people will be still working with a cast iron block than going to billet, and we also want to keep our water jackets as well, because this engine will be still used with coolant in it, whereas for a full drag application, we go with a dry block with no coolant in it at all. So that's what we're going to be doing there. And yes, I do know that there are options from the likes of Bullet Race Engineering that do retain the water jacket, but it's more a case of we thought the 4G63 cast iron block was going to be more relatable there. Okay, so aims for this build, we're going to be looking at something that can produce reliably somewhere in the region of about 1200 plus wheel horsepower. Importantly, probably more important than the actual power level though, is the RPM range. So we need this engine to be able to rev to about 11,000 RPM. My old engine, generally I'd run it to 10.5 on the strip with a rev limit at 11k, and often it would sort of end up touching that. So the reason we need this is the size of turbo that you need to run to make this much power is not going to be making boost particularly low in the RPM range. My old T51R SPL wasn't all in until about 7,500 RPM, which is actually the rev limit for the stock 4G63. So we need to be able to move the engine's rev range up higher. And we're also going to be using cams and headwork that increase or optimize the airflow at high RPM. So in order to make power, we need to make torque at high RPM. The equation, remembering power equals torque multiplied by our RPM divided by 5,252. So the higher in the RPM we can create airflow, the more power we're going to be producing. Now, this engine will be for drag use. It's only going to see short runs and it's going to see regular maintenance and regular teardowns. So we're not expecting here something that's going to go 10 or 20,000 kilometers between teardowns. So that's going to drive some of our decisions. The other aspect here is that it will be running on methanol fuel. And again, that's going to drive some of our decisions in terms of compression ratio. Moving on to capacity. So here, again, just drawing from my own personal experience, I prefer to stick to the 2-litre engine for the drag application. We're going to be making our power not from capacity, but more from the boost pressure that we're running and RPM. And the 2-litre engine, even in stock form, the rod to stroke ratio isn't great. We're going to be working on that in a second. So we don't really want to make that worse by using a stroker crank if we can get away with it. So 2-litre with an 88mm stroke crankshaft, that's the combination we're going to be running there. I've already mentioned cast iron 4G63 block. Now, rod to stroke ratio, particularly as our RPM increases, increasing the rod to stroke ratio can be beneficial. I'm not going to go too far into this. If you are interested in learning more about rod to stroke ratio, we do have a complete webinar in the archive. Search for that and you can learn all about it. But what we want to do is improve that ratio where we can. So what we can do is move from the stock 150mm rod to a 156mm rod, even on the 88mm crankshaft. And what that requires us to do, much like the Evo 9 with a stroker crank, is we need to move that wrist pin higher in the piston to account for the length of the connecting rod. So it's only a small improvement in our rod to stroke ratio, but we'll take everything we can get. Moving on to the engine block. Now, one of the questions here, or one of the considerations I should say, is even with the cast iron block, do we solid fill the block? Now, that's exactly what I did with my old drag engine. We used a product from Moroso, which was a block filling compound. It's essentially a grout or a concrete. We mix it with water, pour it into the water jacket, and the idea here is that it supports the bores, so the bore walls can't flex. It makes the whole block more rigid. Downside, of course, with this is that it also means we can't run coolant through the block. So unfortunately, in our application, because we need to be able to run the engine for more than 8 seconds at a time, we will be retaining a water jacket. We may partially fill the block with block filling compound. The problem with this is the benefits are really in completely filling the block. The most pressure is being created where the piston is nearer to the top of the stroke. So filling the bottom of the water jackets doesn't really achieve the same aim as being able to fill the entire jacket. So we will do what we can do there. In terms of the crankshaft, we will definitely want to move to a billet crankshaft that's stronger than stock given our application here. So we're going to be using an 88mm 7-bolt billet Manley crankshaft. Conrods, so this is an area where we are going to be stepping away from the norm a little bit, and we're going to be using a set of R&R alloy connecting rods. So we'll get these under the overhead shot here, and while this is not a 4G63 rod beside it, still gives you a pretty good indication of the difference we see in the size of the rod. Now, why do we use aluminium? Well, the first is that aluminium is significantly lighter than a chromoly or steel that we use for a steel connecting rod. So that's good. Anything we can do to get weight out of the reciprocating components is a really good thing. However, while alloy is much lighter, it also is nowhere near as strong. So what we end up doing is getting to a situation where in order to get the strength into the rod ends up much larger and a lot more beefy, which is why it looks the way it does. Given the lower density of the material though, even when we add all of this material in compared to a comparable steel rod for the same application, generally we're going to end up with about a 20, maybe a 25% saving in weight compared to a steel rod. So that's all good stuff. There are some other subtle advantages as well. The aluminium material generally tends to absorb shock loading. So what I mean by this is if we've got some light detonation that we encounter, well, of course we don't want detonation occurring in any engine. Sometimes it will occur, and at very high specific power levels. It's basically like someone slamming on the top of the crown of the piston with a hammer. With a steel rod, that shock loading is transferred straight down into the bearing, and it can end up chewing out the bearing very quickly. With an alloy rod, generally tends to absorb that force a little bit. So it gives us a bit more of a safety margin, a bit more breathing room if our tune-up isn't quite on point. Other considerations with the alloy rod though, they will grow a little bit. So the recommendation we need to consider is our piston to cylinder head clearance. We need to increase that dramatically over what we'd run with a steel rod. Now, a lot of people think that the alloy rod stretches in operation, and that's not the case. It is just a case of that the alloy has a higher thermal expansion coefficient than a steel rod, so it simply grows when it's at operating temperature, and that's going to be why we need to allow for that. No free lunches in the world of engine components though, and the alloy rod is no different. While there are a lot of advantages, the biggest downside is that a alloy rod will end up suffering from fatigue related failure. So they have a limited life expectancy, and this really means that they are only suitable for niche applications such as drag racing. While it's very hard to put a specific number on it, obviously it's going to depend on the RPM range, and it's going to depend on the power level the engine subjected to. Drag racers will be throwing these rods away after perhaps 50 to 100 passes down the drag strip. So that's a cost of doing business if you are going to be running alloy rods, and why they would not make for a very smart option for your modified street engine. Next up is our piston. So I've already shown you this a couple of times. This is a Wiseco forged piston. It does have a skirt coating, and it has a coating on the crown as well. One of the features with this piston, which we already kind of looked at, is the very beefy wrist pin. So I've seen from experience with our drag engine program, when you pull the engines apart, sometimes it's very difficult to get the wrist pin out, and the reason for this is that if you don't have a good enough quality wrist pin, it will actually bend, and you'll end up seeing wear in the wrist pin bosses where the wrist pin has bent. So yeah, nice thick beefy wrist pin. Downside of that is it is going to add weight, but unfortunately that's a necessary evil here. Another aspect, and it's going to be really tricky to see on our overhead camera, but hopefully you can, we've got a small series of holes just up above the top ring groove. These are called lateral gas ports. And that's important because those lateral gas ports actually allow the combustion pressure to get in behind that top ring and force it out against the piston wall. And this is a good way of improving our ring seal, and this can help improve power, also reduces blow-by and reduces oil consumption. So lateral gas ports are a really nice feature there. You can also run vertical gas ports. I think I've got a piston here with those. It's not looking that healthy, but I do, so we'll get that under the overhead shot. Please ignore the section of piston that is no longer with us. This is what happens when an injector fails halfway down the drag strip. These are vertical gas ports, basically two ways of achieving the same aim, getting the combustion pressure down behind the ring. The advantage with the lateral gas ports is they don't tend to block as readily as a vertical gas port, particularly on pump gasoline. That's a big issue. You're going to get a lot of carbon deposits, less of an issue on alcohol-based fuels such as E85 and methanol. The last aspect with these pistons is that they are, as you can see, a flat top design. So this increases the compression ratio. We're expecting the compression ratio to be somewhere around about 10.5 to 1 with this engine once it's finished. That might sound scary high for an engine that we're likely to be running 50 to 60 plus psi of boost pressure into. The reason we can get away with that though is because of the methanol fuel. Right, a couple of other considerations with the block. Cylinder head sealing is our main battle here with a drag engine. So anything we can do to improve the cylinder head seal is going to be beneficial. The first of these is that we're going to be increasing the size of the factory head bolts. So in stock form, they're an 11 by 1.25 millimeter head bolt. We're going to be drilling and tapping these to take a 1/2 inch ARP L19 head stud. So the 1/2 inch diameter stud, it's larger in diameter. It's also a superior material, giving much higher clamping load to hold that cylinder head to the block. The other part that goes hand in hand with that though is the head gasket material itself. So I'll jump over to my laptop screen. This is a Instagram I put up a fair while ago of the head sealing solution we've used on one of our customer builds. So this uses a two-piece setup, actually multi-piece setup. The first part we can see here, these are the sealing rings. So these are made out of an aluminium bronze material. They have a little step on the underside of them, and that keys into a groove that's machined into the top of the block. So they key into the top of the block and they seal directly against the cylinder head, and these expand of course as they heat up. Now that's great. That'll achieve one of our aims, which is sealing the combustion pressure, but we also have the water and the oil to consider, and that's where the other part of this gasket, which we can see here, comes in. The rest of the gasket is made out of copper material. Copper material in itself can be used as a gasket. This is used in the likes of top fuel drag engines, for example, with a stainless wire O-ring and a receiver groove. That's fine, but the problem for our application is that copper does a horrible job of sealing oil and water. So this actually has to be used in conjunction with a Loctite product that's applied over the top of it. Otherwise, basically you end up with a bit of a sprinkler system, and you're going to end up with constantly having oil and water leaks between your engine block and your cylinder head. So that's pretty much the go-to solution these days. The likes of Proline use this exact option for head gasket sealing on their ProMod turbocharged engines. Proline also build the Lamborghini V10 engines for the likes of underground racing, again using this exact strategy. It's also what most of the R35 GTR drag competitors are using, so pretty well proven technology, and there are a lot of options when it comes to head gasket sealing. So that's what we're going to be using there. We head back across to my notes for a second here and just catch up. So that leaves us with the head here, and the head really in this instance needs to be a pretty serious deal. We've gone down this path before, so we're pretty well experienced with it. What we're going to be using is a custom grind cam from our friends at Calford. So here we're getting up around the 300 degree duration. So we're looking at cam profiles now that would be more suited normally, or you'd expect to see normally in a naturally aspirated application. And why we can get away with that when we start to run very large turbo sizes, what it does is it reduces the exhaust back pressure down below the inlet manifold pressure. Typically, that's the happy place I like to try and achieve if I can get the exhaust back pressure below our boost pressure. If we can achieve this, we can start using bigger cams with more duration, more overlap, and we can start making the engine essentially respond a bit like a naturally aspirated engine. So this is important because, as I mentioned, in order to make high power, we need airflow at high RPM, and the cam profile is so important with that. Wouldn't make for a very streetable engine. My last engine idled about 1800 RPM, and as I mentioned, didn't really do much until about 7,500 RPM. We will also be including a set of oversized valves here. We definitely want to go to a quality aftermarket valve. Wouldn't be relying on factory valves here. We also need to go to a porting program here. We'll have the head CNC ported. Also important to go with a solid lifter conversion. In factory form, the 4G63 engine uses a hydraulic lifter. Other than the fact that as they get older, they can become a bit ticky. Nothing specifically wrong with them. They work quite well, but in a drag application, the hydraulic lifter is not compatible with a two-step launch control strategy. What will happen is that the aggressive popping from the two-step launch control, will end up popping the exhaust valves back off the seat while you're building boost. That allows the hydraulic lifter to pump up, and then you lose all compression on that cylinder. So we're going to be converting to a solid lifter. It's also important when you are choosing components. If I can get my words out here, you need to make sure that the cam profile, that's what I'm looking for, the cam profile that you choose has to suit a solid lifter. The cam profiles are different between mechanical and hydraulic lifters, so you can't run a hydraulic profile, for example, with a solid lifter, or at least you shouldn't be. Right, we're going to move into questions in just a second. Looks like we've got plenty of them there. The last thing I'll mention there is we're going to be now needing to be a lot more careful about our valve spring selection. Again, this can be chosen in conjunction with the cam supplier. This case, we're probably going to be looking at a double valve spring as opposed to the more common street level sort of beehive style valve spring, and we're going to be needing to be very careful about making sure that our seat pressure and our pressure over the nose is exactly where it needs to be to control the valve at 11,000 RPM with the lift and duration of those cams. All right, let's get into those questions and see what we've got here. Stuart has asked, interested to hear your thoughts on when to choose forged pistons for a naturally aspirated engine. Price is a huge factor, $200 versus $1,000 for a set. Okay, that is actually a really good question, Stuart, and this really comes down to one of those areas where quite often you can end up spending more money than you really need on parts that you just don't require. So the factor for when a factory cast piston becomes basically unreliable is the point where it cannot handle the cylinder pressure. The other factor that will very quickly destroy a cast piston, though, is detonation. Detonation will end up breaking ringlands in a cast piston. So what this means is that good quality tuning is absolutely essential to get reliability out of a cast piston. If your tune-up is on point, you can quite often go a lot further with a cast piston than a lot of people think. Case in point, our Toyota 86 with the FA20 turbo engine in it. That engine, despite the fact that I have replaced the connecting rods, the factory connecting rods weren't up to what we were trying to do. With a turbocharger on it, last time I had it on the dyno, it's making 385, 390 wheel horsepower. Now in stock form, that naturally aspirated engine was rated at 200 flywheel horsepower. So safe to say we're at or about double the factory power level on a stock cast piston. We've got no detonation occurring and the pistons are still really healthy. So that's the first factor to consider there. Now, there are some engines, unfortunately, where the pistons are well known to be basically made out of glass. So if you've got an engine where common piston failures are occurring, even in lightly modified applications, then obviously that's a different factor, but that would be the exception rather than the rule. Getting a little bit long-winded here, Stuart, but the other consideration here where you really would need to go to an aftermarket piston is, do you want to start getting some more compression into the engine? Obviously, at that point, you're going to need to go to a different crown profile, and a forged piston may be sensible. But in most instances, for lightly modified engines, naturally aspirated, the factory cast piston is probably actually just fine. Next question comes from James, who's asked, when you replace the OEM oil pump gears, is it necessary to replace the oil pump housing at the same time? Okay, pretty open question there, James, because it's obviously going to depend on the application, and there are both instances. So there are some aftermarket oil pump gears that are made to go inside a factory housing, and then there are other complete standalone aftermarket oil pumps that have their own gears. So very dependent on that. If you are purchasing gears solely for your existing housing, it is really important to make sure that the housing is in good condition, that it isn't showing excessive wear. Otherwise, you run into a problem where the gears may be strong and may not fail, but the oil pump housing, if it's seriously grooved, you are going to end up with internal oil leaks, and you may end up low on oil pressure. Next question. I've always wondered if there was a huge difference between Chinese rods and American name brand ones. It's often a difference in almost double of the price. Yep. It's a difficult one to answer because I can't make a blanket rule here. I've been in the industry for long enough to see some absolute garbage products come out of China, but unfortunately you can't really say that everything's garbage, because there are also some really good quality parts at a really, really good price point. So if you are looking at Chinese rods though, I would make sure that you are doing your research and seeing what experience others have had with that same brand of rod. Now there's two factors to consider here. I've already mentioned the fact that there aren't really a lot of fly-by-night companies setting up manufacturing plants to build forged connecting rods. It's a lot of work and a lot of capital, so these companies generally are in it for the long haul. So there's the manufacturing process, that's one consideration, but the other factor that will affect the outcome of your finished rod is the raw materials that go into it, and not all raw materials are made equal. So some of the more high-end rods from the likes of Carrillo, they have a lot of processes they go through in terms of how they purchase the raw material, so that it's a known guaranteed quality, and then checking it for internal flaws during the manufacturing process. You're probably not getting that on some of the Chinese rods. So again, can't really sort of lump everything into one bucket and say that they're all garbage, because unfortunately that's not that simple these days. Breach 89's asked, what bore size should be run on the head gasket if the cylinder was oversized by 0.5 millimeter? Like, there isn't a absolute rule here. What we want to do is make sure that the head gasket bore is definitely no smaller. Otherwise, we end up with a situation where the head gasket is going to protrude out into the combustion chamber. It could end up being melted or damaged. It could become a hot spot. So generally, we always want the head gasket to be at least the same size as the bore. It's generally actually going to be a little bit larger. So maybe around about 1 millimeter larger than the bore diameter. Most head gasket manufacturers, though, aftermarket head gasket manufacturers will have gaskets on the shelf for bore sizes to suit a bored engine as well. James has asked, are block guards worth installing during the engine rebuild? Pretty common option, or at least they were back in the Honda B series days. I've used a few of them. The reality is I don't think the older style block guard, which is what I've just mentioned there, that was used with the Hondas, these aren't really that much use. I think they're probably more of a case of making you feel better about the process, and in some instances they can end up actually being a detriment. Those block guards, you didn't do any machining to the block water jacket. It was just a gentle tap fit down in the water jacket, and basically the idea is it supports the bores. The problem with this is because the water jacket, the block wasn't machined to accept the block guard. It also created pressure points where it touched the bores, and it can end up distorting the bores. On the other hand, I don't call these a block guard, I call them a deck plate. We've actually gone through this process on our own FA20, an engine I haven't even put together yet. This is a case where an open deck block is machined to accept a deck plate, which is like an interference fit. It might have a 1 to 2 thou interference, and it is pressed into the block. So because it is a very tight fit, that is going to support the bores properly, and in a high performance build, those are well proven to be worthwhile, but there are a lot more expense involved in the process. Next question, at what point are forged rods preferable in a high compression or motor situation? What is the increased strength worth more than the increased weight? Okay, that's a difficult question to answer because it really is going to come down to the quality of your existing rod. That is where getting some hard data points from others building similar combinations and proving where the factory rods fail is the preferred option. Now, again, if you're dealing with a popular engine, that will be 100% something you will be able to get information on. So basically what I'm saying here is, yes, if you haven't got an engine where the rods are known to be a failure point at your power and RPM level, then there's absolutely no need to change them. If you are increasing the RPM, even on a cast rod, then it is quite worthwhile considering a move to an upgraded fastener. As I mentioned, there's the compressive forces and the tensile forces. Both of these need to be considered. Bjorn's asked, with 50 psi running methanol fuel on such a high compression ratio, if on pump gas, what amount of psi would you generally be able to get away with? 10 to 1 compression or 10.5 to 1 compression on pump gas. Yeah, you could probably get maybe 10 or 12 psi of boost into the engine, but you'd be fighting to stop it from detonating even at such low boost pressure. The 4G63 engine in general doesn't like a lot of ignition timing and doesn't need a lot of ignition timing anyway, and as soon as the compression ratio sort of exceeds about 9, maybe 9.5 to 1, the engines become very, very knock sensitive. So yeah, you could get the boost in there, but you'd be just fighting to stop it knocking by retarding timing. Next question. Kelly's crank scratches on journals was polished after a season of racing a 1500 horsepower car. The bearings have scuffed from high spots on the crank. Should I polish the crank again or look into another crank? Okay, basically, when you're assessing the crankshaft, there's two aspects you need to look at. Let's call it three aspects. The first is checking the crankshaft to make sure that it's still straight. So this can be done with V-blocks and a dial gauge, where you can get your machinist to do that. So that's number one. Second factor is just checking the journal condition. So you mentioned there's some scratching there. It depends how bad that scratching is. Quite often the scratching looks worse than it is. My guide is, if I can feel it when I run my fingernail across it, then it's going to need some attention. What that attention is going to be is going to depend still on the depth of those scratches. In some instances, a light polish is going to be more than enough to remove those scratches. In some instances, the crankshaft may need to be ground. So yeah, grinding crankshafts is another contentious subject because you can recover a crankshaft and get another life out of it, but crankshafts generally will also have a surface hardening that doesn't go very deep into the crankshaft. So as soon as you grind the crankshaft, you're going to grind through that surface hardening, so you can expect increased wear. So yeah, a bit hard for me to say without knowing a little bit more information about that particular crankshaft. Sorry, it's probable that you could recover that crankshaft though, as long as it's not cracked. Cracking was the other aspect I didn't mention there. Need to also crack test the crankshaft and make sure that there aren't any cracks in the fillet radius. Redneck with Tech has asked, when's it a good idea to change the oil viscosity you're using in your build, example for being a street or rallycross car? So what this comes down to is looking at your oil pressure. Generally, with a performance build, the process that I'll go through is to build the engine with slightly looser clearances than factory. This might be somewhere in the range of a quarter to half a thou of additional clearance, and this just allows me to get allows the crankshaft to flex without ending up with metal to metal contact. When we do this though, we also need to go to a heavier viscosity oil. Otherwise, we're going to find that our oil pressure is insufficient. So the two kind of go hand in hand together. Eric's asked, what's the safer upper power limit for a 4032 alloy piston? Look, it's probably not that simple, unfortunately, Eric. It's very difficult to have specifics for these. It's going to depend on the engine itself, but so much of this is going to depend on the quality of your tuning. 4032 pistons, I think, are actually overlooked in a lot of instances, and they have a lot of upsides that people tend to ignore. For those who aren't aware, a 4032 piston is a forged piston made from a different alloy than the more common 2618 that we see, and it sits sort of somewhere between the factory cast pistons and the 2618 piston. The advantage with the 4032 is that it's stronger than a cast piston, and it also has a lower thermal expansion coefficient due to the silicon content in the alloy compared to 2618. So what this means is that we can run tighter piston to cylinder wall clearances, and that's a really good thing for a street engine in particular. It is, however, a little bit more brittle than a 2618 piston, so it's not the ultimate for a very high horsepower build. Where I was going with this though is, again, if you've got a good quality tune-up in the engine and you're not running it into any level of detonation, the 4032 alloy is actually going to last really, really well. All right, our next question comes from Bob, who's asked, not personally having any experience with turbo motors, when, if at all, do you end up adding O-rings to the block, starting at what boost levels, and in the case of open deck, what's done, if anything? Okay, so this is an area where there's so many different experiences and opinions on what works and different processes to go through. There isn't a point where I can say at this power level or this boost pressure we must O-ring the block, because it will depend so much on the block construction itself, whether it's alloy, whether it's cast iron, the rest of the engine components as well. So there isn't a sort of a fixed point where we need to do something. It really comes from experience and finding at what sort of boost and power levels are we starting to have head gasket integrity issues. I was a big fan with our original 4G63 drag builds of using a stainless wire O-ring that I put into the block, and I coupled this with an MLS gasket, which is a little unusual. We used a small amount of protrusion, and that worked really, really well, gave us a nice advantage. The other hand, as I mentioned earlier, the top fuel method is the copper gasket, which is nice and malleable, and then they use that with a stainless O-ring in the cylinder head and a receiver groove in the block, and it basically distorts the copper gasket down into the block itself. I haven't found that technique with the copper gasket works too well on our smaller capacity sport compact engines. Not 100% sure why I could sort of say that's the case. The other aspect you've asked there, what do we do in the case of an open deck block? Well, that kind of comes back to if you want to go and make that a bit more robust, two options there. You can add a deck plate, which is what I was talking about before, a plate that's essentially machined that fits into the water jacket. It requires machining, extensive machining to the block surface to allow that to fit in with the correct amount of interference. Or alternatively, for common engines, the likes of Darton make ductile iron sleeves that incorporate basically the deck surface as well. They locate out to the outside of the block. A lot more money involved in doing that as well. Hotshot Havens asked, do you consider piston deck thickness when choosing to move the pin closer to the top? You do need to consider this, but this is something that's more in line with what the piston manufacturer is going to do. The deck thickness, or the crown thickness, though, if we look at this piston from the side here, we can only move the wrist pin up so far in the block, in the piston, because otherwise we're going to get to a point where it's going to start interfering with the second compression ring, and we can't intersect the second compression ring. Likewise, we can't move the ring pack too far up on the piston because that doesn't work well with the turbocharged application. So generally the ring pack is really going to define how far we can move the wrist pin, and as long as the thickness of the small end of our rod is not too significant, that's not going to cause us too much of an issue. So ring pack is more of a driver of that than anything else. Right, we've got another question here from Dustin, who's asked, any plans to build a 3S GTE? Look, at this stage, probably not. It's not one that we've been asked for. Probably an engine now that is getting a little bit long in the tooth as well. Richard has asked, seems aluminium rods are common in the US for street cars. Now, what are your thoughts? Look, you can get away with it. It's very difficult. Even the rod manufacturers themselves don't have a strong line in the sand of exactly when the rods need to be replaced. I think they tend to err on the side of caution. Obviously, they don't want to say it can do X number of miles of use, because if it fails prior to that, they kind of end up with egg on their face and potentially an expensive lawsuit. For me, at least, the potential downsides in terms of maintenance just aren't worth the upsides for a street engine. I'll stick a set of steel rods in a street engine every time and be happy that I don't have to replace them, and I just don't have to worry about them. I don't want in the back of my mind every time I do a full throttle pull through the gears, is a rod going to exit the block at 8,000 RPM? Next question, or last question for today. I'm building a Fuji 63 Evo 7 engine using a 94mm stroker crank, target wheel horsepower 900 on ethanol. What compression piston should I use? Also, I'll be using a Precision 6870. What size turbine housing would be better? Okay, so compression ratio. Now, it depends if you are going to be purely on ethanol or you're still running flex fuel. If it is a specific build for ethanol or E85, I would generally bump the compression up a little bit. When I go crazy, 10 to 1 thereabouts would be fine. There are 10 to 1 compression E85 pistons available from the likes of JE. I know they do a shelf stock piston for that style of build now because it is so common. I can't give you much information though on that 6870. The reason for that is I simply have never used precision turbos, so I don't have any first-hand experience on that particular turbo. That was just a taste of what we put on every week for our HPA Gold members. Our Gold members are able to watch these live and ask questions and get answers while we're presenting. After the webinars have been hosted live, they're added into our webinar archive where our Gold members can rewatch them at their leisure. We've currently got over 240 hours of existing webinar content covering topics on engine building, engine tuning and wiring. This is one of the fastest ways to expand your knowledge on a wide range of topics, as well as to stay up to date with the latest tools, trends and techniques in the performance industry. Our Gold members also get access to our private members-only forum, which is the best place to get fast answers to your specific questions. Gold membership can be purchased for just $19 per month. However, you'll also receive 3 months of free access with the purchase of any of our courses. Click the link in the description to learn more.